Okay. I misspelled building. Isn't that embarrassing? Well, anyway, what we're going to be doing in this section is building linear models from data. So scatter plots. What is a scatter plot? Well, if we have raw data, like we do in this example here, and in any other kinds of examples that involve raw data, usually you want to draw a scatter plot. And all a scatter plot does is visually represents the raw data on a coordinate system. That's really all it does. And what's the point of drawing a scatter plot? Well, scatter plots allow us to see what kind of relationship exists between the variables, or between two variables, I should say. Should be specific. So when we make a scatter plot, that'll allow us to see what kind of relationship exists. And, in this section we have linear models, but, we also have other types of models besides linear. We have quadratic, cubic, exponential, and so on. So scatter plots give us an idea of what could be made. All right, well, in this example, we're looking at the relationship between Major League Baseball teams, so their on-base percentage and the runs scored. For teams in the National League during the 2014 baseball season. So if their on-base percentage for Arizona was 30%, 30.2%, 615, and so on. So using a graphing utility, draw a scatter plot of the data. So this is a calculator exercise, and I'm going to go show you how to do this in your calculator. Each one of these, you got to get this in your, you got to get this data in your calculator. So the way to do it is you can press the Stat button right here that you see. Press the Stat button and go to Edit. And in these lists, you're going to type in your data. So in list 1, you're going to type in your X data, and in list 2, you're going to type in your Y data. So just type it in. So 30.2, so I'll just go through it, the process. You should go through the process as well. Alright, so that's the X data, and I'm going to type in the Y data. So I'm going to take my arrow and just go to the L2. So 615 and so on, you can type that in. Make sure you type it in order. Alright, so I got all my data in. So now that my data is in my calculator, I want to make a scatter plot. So what I have to do is I have to turn the scatter plot on in my calculator. So if I press y equals, I want to make sure that any equations that are in y equals are gone. So get rid of them first. And now you want to turn your stat plot on. So right above y equals, you see the word stat plot. So hit second, y equals. Now you want to turn one of these on. So just turn the first one on. So hit enter there and turn it on. Just hit enter on. By default, the first thing, the type that you see here, the first thing highlighted is the scatter plot. By default, that should be labeled, but if it isn't, make sure it is. You know, you have all these other types of plots here, like your calculator is capable of making all kinds of plots. This is a time series plot. This is a histogram. This is a box and whisker plot if you've taken statistics, but yeah. Make sure your data is in L1 and L2. By default, it should be. And this just means, you know, this will show you what kind of dot or order pair will be made. The big thing is you want to make sure that it's on. Once it's on and your y equals is clear, now I just got to graph that data. So to do that, you just go to zoom, which is right here, and you go down to number 9, which is zoom stat. Or you could press number 9. And there's your scatter plot. Here's your x-axis. Here's your y-axis. So there's your scatter plot. So that's the answer for question 1. You know, make sure that you know how to do that in your calculator, because that is an important technique to do it. But let's go on to question 2. And the question 2 asks, describe what kind of relationship exists between the runs scored and on base percentage. So if I look at my scatter plot, you know, this is my scatter plot. I'm trying to see what kind of relationship exists here. And if I look at my scatter plot, in general, I could probably make a line that goes through this data. All right? If I used a line that goes right through this data somewhere, I could probably use a line to describe this data set. So what I'll say here as an answer is based upon the way the data is exhibited or is presented, the data seems to have a linear relationship. And it's because I could use a line here to accurately reflect the data. Okay. So if I go to the next page, I actually give you a much more accurate scatter plot of the data we just made. There it is. But, you know, I want you to be able to recognize what linear versus nonlinear data looks like. Because in the future sections in Chapter 4 and in other sections, we have other types of modeling. You know, we have other types of data. This data here is obviously, this is nonlinear. Because that data doesn't look linear. It kind of, if I were to use a model to approximate this data, like this, for example, that would probably be quadratic. Because that looks like a parabola. Now this data would be linear, because I could usually use a linear model to represent that data. Right? That looks like it could follow a straight line, which is linear. There's this thing in your calculator. It's called a correlation coefficient. And you'll see what I mean in a minute. but the correlation coefficient is usually denoted by R or R squared, depending on what kind of modeling you're doing. And it takes the value between -1 and 1, or if you're looking at R squared, R squared takes the value, it's anywhere from -1 to 1. And what the correlation coefficient measures is it measures the strength of the relationship between the two variables. Okay. So what does that mean by strength? Well, you know, if it's linear, quadratic, cubic, whatever model you're using, it means a better approximation. So in this case, this is a pretty strong linear relationship. This is a pretty strong quadratic relationship. But I would definitely not say that this is a strong linear relationship. This is a very weak linear relationship. Just like this one would be a very weak quadratic relationship. So what I could say is the closer R or R squared is to -1 or 1, the stronger the relationship is. And the closer R or R squared is to 0, the weaker the relationship is. So what does it mean if one of them is +1 or -1? Well, the value, whether it's positive or negative, doesn't change the strength of the relationship. It just means if it's positive linear or if it's a positive model. So +1 means it's positive, which means it's increasing. Negative just one means it's negative, which means it's decreasing. But regardless, the closer to 1, the stronger the relationship. The farther away from 1, or the closer to 0, the weaker the relationship. So for example, this, if you were using a linear model to approximate this data, your R value would probably be pretty close to 0. So it would be something like 0.05. I'm just picking a number that's close to 0. But if you were using a quadratic model, which this thing looks very close to, your R value might be like 0.97. So that's what the correlation coefficient measures. Okay. So on the next page, what I ask you to do is, using that baseball data again, that describes the data by selecting 2 ordered pairs. So what I'm going to do here is I'm going to I'm going to select two ordered pairs myself from that data. So pick 2 points and find the linear model. Now, before I actually pick 2 points, let me ask you this question. How do I know which 2 ordered pairs I should pick? How do I know which 2 ordered pairs I should pick? Well, this is why they call it modeling. Because when you're doing modeling, you're approximating the data with a known equation. And that's what modeling is. It's an approximation. It's a replication. So what I'm doing is I'm looking at my scatter plot, which is right here. And my goal is to pick 2 data points that will make a line that will come as close to the rest of the data points as much as possible. So, you know, I could pick any 2 data points I want technically, but I could pick 2 better data points than 2 others, right? You know, 2 data points would give me a better linear approximation than 2 other ones would. So let me just say this. So preferably, you should pick 2 points from the, quote, inner, end quote, portion of the data. So you don't want to pick the first point, and you don't want to pick the last point. You don't want to do that. This process, picking inner points of the data, that's called interpolation. So if you're using the process known as interpolation, you're picking inner points from your data. Now, so I'm going to pick two points that come as close to all the other data points when a linear model is made. Now, when I did this, so, you know, you could pick 2 points, but I could pick 2 other points. They'll describe the data, but one linear model might describe the data better than the other one. There's multiple possible models here, and they all do a decent job, but one of them might do a better job than the other ones. It's similar to when you're watching a weather forecast for like a winter storm, right? If there's a blizzard coming or a nor'easter, you know, MSNBC might be saying we get 12 to 24 inches. Fox News weather might say we get 18 to 20 inches. CBS might be saying we get 20 to 28 inches. You know, each forecast has its own, each, you know, broadcast has its own potential forecast, but, you know, one of them might be more accurate than the other. So that's what's going on here. You know, you gotta look at all the forecasts and make an informed decision and say, okay, we're probably going to get about 20 inches of snow because all these forecasts are in the same ballpark. So there's nothing wrong with CBS or Fox's or MSNBC's snowfall forecast. All of them are pretty accurate, but, you know, which one you take is really just a matter of preference within reason. You know, you wouldn't take a forecast that says we're going to get 50 inches of snow. That might be outlandish, but you would pick something that's reasonable. So when I did this, I picked the points. So on my scatter plot, I picked point number 7. So 1, 2, 3, 4, 5, 6. There's actually 2 here. 6, 7, and 8, 9, 10, 11, and I picked point 12. So those are the 2 points I picked. But that's not to say that if you pick point 6 and point 10 that your model would be wrong. It just, you'd have a different approximation. So the points 7 and 12 on the data set correspond to, let me go back to the data. So that's going to be that's the LA Dodgers data. That's number 7. And Philadelphia. Hey, that's nice. That was point 12. So those are my 2 order pairs that I used. So I'm going to use those 2 order pairs. This order pair and this order pair to find my linear model. So let's do that. So those are the points, what, 31.7 comma 645 and 29.2 comma 535. So find the linear model between those 2 points. So the slope, y2 minus y1 over x2 minus x1 equals, so y2 is going to be 535 minus what? 645 over 29.2 minus 31.7. So when I take out my calculator, so I can clear that out, let me get out of there. 535 minus 645 gives me negative 110 over 29.2 minus 31.7. That gives me negative 2.5. So negative 110 divided by negative 2.5 gives me 44. So my slope is 44. I have 2 points. I could use the point slope form. Y minus y1 equals m times the quantity x minus x1. So I'll pick this order pair and with this slope. Just make sure you pick from one of the 2 order pairs that you used. So y minus 645 equals 44 times the quantity x minus 31.7. So distribute the 44x minus, so 44 times 31.7 gives me that value, so 1,394.8. Add 645. So y equals 44x. So minus 1,394.8 plus 645 gives me negative 749.8. So this is my linear model, or it's a linear model. Remember, there are multiple linear models out there, but this is the one that I picked between these 2 data points just from observation. And there's nothing wrong with this model. It's perfectly fine. It does a good job of representing the data. But let me ask you this question. we would prefer to get the best model, right? How do we know which one is the best model? How do we know? What's the best model for the data? You know, how do I know that this is a good model or not? Well, your calculator could do something called finding the line of best fit. And the line of best fit basically line of best fit or linear regression equation. The line of best fit or the linear regression equation is the best possible model for a given data set. So since we're dealing with linear regression, we're going to use the linear regression function to find the best possible model. It gives you the best approximation. So while this model is pretty good, it's not the best model. We're going to find the best model. So on the next page, I say using the same baseball data, find the line of best fit and graph it on the scatter plot. So my scatter plot that I had here, I'm going to find the line of best fit and then I'm going to plot it on here. And I'll actually plot the line I found by hand and the linear the line of best fit simultaneously to show you how they compare. All right, so this is how you find the line of best fit. So pay attention to this in the video because this is a handy trick. So to find the line of best fit, you're going to press the Stat button again. You're going to go over to Calc. And when you go over to Calc, don't confuse this calc for this calc right here. They're two separate calcs. This calc is underneath the Stat button. So when you press Stat, you go over to Calc. And if you go down to number 4, here's all the different regressions that we have in our calculator. We're concerned with linear regression right now. So hit Enter on that. Now, here's where you may see something different or not, depending on what kind of calculator you have. If you have a TI-84 calculator, obviously this is what you'll see. If you have a TI-83 calculator, you will not see this. So just bear with me for a second if you have a TI-83. So those of you who have a TI-84, all you have to do is make sure your data is indeed entered in L1 and L2, and then you could go down to Calculate. And then, boom, it gives you the line of best fit. Which, in this case, if I round it to the to the hundredths place, so the line of best fit is going to be y equals the slope, is the a value, which is 38.02, x plus b, which is minus 544.86. So that's the line of best fit. Now, since I don't have a TI-83 on me, I got to describe this in words. If you have a TI-83, when you go to Stat and go down to linear regression, when you hit Enter on linear regression, that word, linreg ax plus b is going to show up on your main menu, right? You won't see this. You're just going to see that name. What you're going to do when you see that name, you're going to have this. You're going to have lin reg ax plus b when you hit Enter on that list. What you're going to do is you're going to type L1, comma L2. So L1 is right here above the number 1. So you just hit second. What you would do is you would hit second L1, comma, the comma button's right here, comma, second L2. And if I hit enter here, it's not going to give me anything. It's just going to give me an error message. But that's if you have a TI-83. So you go to stat, go down to linreg, and then you hit L1, second 1, comma, second 2 to get L1, comma, L2. Then when you hit enter, you should get the same values I just had. You know, the TI-83 is more outdated than this, so it requires a little bit more finesse. But anyway, there's my linear regression model. Now, you could spit out the correlation coefficient here if you want to. It's not necessary. If you don't do it, it's not a big deal, but I'll just show you what it looks like. So to get the correlation coefficient to show up, you have to access the catalog feature. So press second 0 to get the catalog. This is just like a glossary of everything your calculator can do. So I'm going to go all the way down to diagnostic on. I'm going to hit enter on that, and then I'm going to hit enter again. So what that does is it puts your calculator back into standard mode. So now if I go to stat calc and I go down to linreg and I get it, it should display the R squared and R value. Now when you're dealing with linear regression, you deal with the R value. So this is 0.85. So, you know, 0.85, or well, if I round it to 0.86, that's a pretty decent relationship. It's not the best, but it's a pretty good one. You could also, you could store this, the calculator you get, you could store this into a variable. So, for example, if I want to store this in Y1, for example, and plot it, you have to get Y1 into that store. So what you do is if you go to stat calc, hit linreg, you got to go to store reg equation. You just have to type Y1 in here. So to get that, you need to get to the variable button, which I believe is under stat. Hold on, I got to figure out where the variable button is. Just bear with me for a second. I want to get Y1 there, so I know where it is. I'm just having a brain fart here. I think it's insert. No. It's not a big deal if I don't get it, but where's the variable? It's under var. There it is. I'm an idiot. I'm sorry. Vars button is right here. See this vars button? You hit vars. Go over to Y vars. And I know that if you go to function, you can, you know, you go Y1, Y2. You could just store it in the Y1 function. So if I store it in there, I calculate it, now it's going to be under Y1. So you don't have to type it in that way. And now if I graph it, it'll look really nice on my model. So there's my linear, that's my line of best fit. And you know, if I type in the line that I found by hand in Y2, just by comparison, which was 44x minus 749.8. So there's my line I found by hand. Notice how it, it does approximate the data, but this one up here, this one right here, seems to be a better approximation. That's the line of best fit. And obviously we want the best model. So this is the best model. And the one we found, the approximate model, was y equals 44x minus 74.98. So this is the best. This one is, it's okay. It's not bad. We want to use that one. And if I want to interpret the slope, that's the slope, right? So remember, slope is rise over run, 38.02 over 1. And in this problem, right, the x variable was the on base percentage, right? This was on base percentage. This right here was the number of runs scored. So if I want to interpret that, what I could say is 38 runs were scored for every percentage, just like 1% increase. So I'll just say percentage increase of base percentage, or of on base percentage. So I'll say for roughly 38 runs were scored for every 1% increase of on base percentage. Or you could also say for every on-base percentage, the number of runs scored increases by roughly 38 runs. And if I want to use the line of best fit to predict the number of runs a team will score if their on-base percentage is 31.5, then that means I just want to find x, or I'm sorry, I want to find y when x is 31.5. So plug that into my linear model of best fit. And you can actually evaluate that. So I stored y1. I went to calc, linreg. I stored it in y1. So that was under vars, yvar function y1. You could actually, if you go to var function, you could type y1, and then you could just use the parentheses for the input as 31.5. Now I'll give you the value evaluated now, which is 652.67. So when the on-base percentage is 31.5%, roughly 653 runs are scored. And I rounded up because, you don't score a decimal amount of runs in baseball. So, you know, this is more of like a calculator exercise, this section, but this gives you an idea of how to use linear modeling, and going forward, all kinds of other modeling techniques. You know, making a scatter plot, making the model of best fit. We were looking at linear models, but there's also quadratic models and cubic models and so on. So, yeah, that's the end of this section.